Hey guys, this lesson is for Calculus BC. This is 10.4, and this is applying calculus to polar functions. So the first thing that I'm going to do is I'm going to refresh your memory on some of the details that you learned about polar functions from pre-cal. If you ever want to see the full extent of that content, you can go back on my videos on the pre-cal from 6.3 to 6.4, okay? But here's a brief recap, and let's start off with what it looks like on a graph. This is what a polar graph looks like, where r is the distance from the pole, so it's really just the number amount of rings out. And then theta is like your unit circle. It's that angle counterclockwise from the polar axis, also known as the x-axis, okay? So, for example, if I wanted to represent this point, I know that on my unit circle, this direction is pi, and I'm going 1, 2, 3 rings out, so I can call that 3, pi, okay? Now, because we have the polar graphing system and we have the rectangular, we can convert back and forth between the two. We have this image visible here so that you can see this same exact spot. In blue, I put rectangular, and in red, I put polar, okay? So the formula is that you can get your r comma theta from polar and turn it into rectangular x comma y by plugging the r's and the thetas in these formulas. Now it should be easy to remember because on your unit circle, you know that cosine is your x and sine is your y. So x is r cosine theta and y is r sine theta. Now if I want to go in the other direction and convert my rectangular to polar, my x comma y to r comma theta, I can plug in my x and my y's into either of these two formulas. Okay, I like this right one because it already has theta isolated, and I do the inverse tangent of y over x. If I need my r, I can use Pythagorean. I like this one better because it has r isolated, which is just square rooting this r, and then I get my r. So the fact that I'm using Pythagorean should make sense because the r is the hypotenuse to these right triangles that you see here, okay? So we're going to take a moment, do a few practice problems from pre-cal, and then we'll be moving on to the calculus. Let's take a look at this first example. It says convert polar to rectangular. So that means what I have here, if this is polar, is my r comma theta. So I am going r comma theta to x comma y. Okay, here's my r and here's my theta. I know my formula for x is r cosine of theta, so I can say 2 times cosine of pi. I know that cosine of pi is -1, so I can say 2 times -1, which gives me -2. Okay, now for my y, I know the formula is r sine of theta, which would be 2 times sine of pi. Sine of pi is 0, so I'd say 2 times 0 is 0. And now my ordered pair is -2, 0. If you are ever in doubt, guys, graph it, okay? I know if I'm talking polar, this would go 2 rings towards pi. So pi is over here, and I would go 1, 2 rings over. Okay, this is polar. And now rectangular, I know -2, 0 goes 1, 2, and then I don't move up or down. My dot would be here. Can you see visually that the graphs look the same even though one's polar and one's rectangular? It's a great way to help you double check. Let's take a look at another one. Okay, we have square root of 3, pi over 6. Again, we can tell just by the pi that this is polar. So I'm going r theta to xy. If x is r times cosine of theta, I can say square root of 3 times cosine of pi over 6. Pi over 6 on the unit circle, cosine of it is going to be radical 3 over 2. So I have this radical 3, right? Times the cosine of pi over 6, which is the radical 3 over 2. When I multiply those two together, radical 3 times radical 3 is just a 3, and then I can put it over 2. My y value is r times sine of theta. So I have square root of 3 times sine of pi over 6, which gives me square root of 3 times sine of pi over 6 is half. And that gives me square root of 3 over 2. Now, let's go ahead and look at these next ones. We can also convert equations, not just points, okay? So I want you to first be able to describe the graph and then confirm it by converting. So if I think about r equals 2, r represents the rings. So if they say the full equation is r equals 2, that is probably me just drawing completely on that second ring. Okay, so let's say it's me tracing the second ring, which would make a circle. Just on this one, I'm going to change colors so you can see it a little better. Just on this one. Okay, so if we convert, I know based on my formulas, I know that r is equal to square root of x squared plus y squared. So I'm going to replace that r in terms of x and y. And now, hopefully, if you remember, okay, this looks like a circle. I know my circle equation from pre-calc and even from algebra 2 is x squared and y squared. Let me get rid of that radical. I can do so by squaring both sides. And now I can see the equation of a circle with the radius being 2, which confirms the drawing that I had done when it was in polar form. Let's move on to the next one. I know that theta equaling pi over 3 is a line. If I think of my unit circle, I know that pi over 3 is up here. So if my equation is just pi over 3, that is probably a line that just goes through pi over 3. So that means when I convert it, I'm probably going to get something that looks like a linear equation. Let's check it out. I know that I have a formula that says theta equals inverse tangent of y over x, or I can use the formula when it's written as tangent of pi equals y over x. So I can plug this theta right here and say tangent of pi over 3 equals y over x. Well, I know that tangent of pi over 3 is equal to square root of 3. And I know that when I'm in rectangular form, I want to isolate my y. So I'm going to multiply my x over, and I could say y equals square root of 3x, which this makes a linear function. It's to the first power, positive slope. My slope is just square root of 3 over 1, which matches a positive linear slope with what I had drawn when I was analyzing as a polar function. Okay? Now for this last one, I have the equation r equals secant of theta. When I think of this, I may not know what this is going to look like in polar. So here I'm going to be forced to convert and then analyze the graph. So when I think of the formulas that I have to convert, I don't have one with secant, but I do know I can rewrite secant as a cosine, and I do have a formula for cosine. So for example, I can say r is equal, instead of secant, I could say 1 over cosine of theta. And now I know off the top of my head that I have a formula that has r and cosine together. So what I'm going to do is I'm going to want to multiply that cosine to the other side and say r cosine of theta equals 1. And then r cosine of theta is x, so I can convert it and say x equals 1. And now I know what the equation of x equals 1 is. Rectangular, it's on 1, it's a vertical line. Okay. So that just means if I were to draw this in polar, wherever my ring 1 is, it's just going to be a vertical line right there. Okay. So let's look at the next thing I want you to recap from pre-calc, and that's what your polar graphs look like. Okay. You're not going to necessarily find yourself having to graph these in detail, but at least to be able to recognize what a quick sketch could be or what just overall it's going to look like in order to take that next step and apply the calculus to it. So the first type of polar functions that you have are circles, okay? If you would like to see this in detail, you can watch the video from 6.4 from my pre-calc videos, okay? So circles is when you have a number times the trig function. Notice that cosines, like the x's, are on the right or the left, okay? Notice a positive cosine, just like the positive x's, is on the right, and a negative cosine, like a negative x, is on the left. Sine is like my y's, so a positive sign is on the top, and a negative sign is on the bottom, where a, that coefficient, is the diameter of this circle, okay? Next, you have Limassons, okay? Limassons have a number being added or subtracted. Sorry about that, just noticed the equations weren't written down. I paused a moment and wrote them. So you would have a number plus or minus and then the circle equation with cosine or sine. The four examples drawn here, because it is majority on the right, we can assume would be the scenario of a plus b cosine. If it was a minus b cosine, it would be one of these images, majority on the left. A plus b sine would be majority up top. A minus b sine would be majority on the bottom, just like the scenario with the circles. Now, the different types of Limassons are dependent on the ratio between a and b. If a over b is less than 1, we have this loop. A over b is equal to 1, we have the cardioid, which is the heart. If the fraction a over b is in between 1 and 2, it's the dimple. And if it's greater than or equal to 2, it just has like this, it's just less of a dimple. Notice it gets smaller to the heart, smaller to the dimple, and an even smaller dimple, okay? The extent of these details I wouldn't stress about. Just know if you have a loop, it's going to make a big difference, okay? Next, you have rose curves, okay? And those functions is when the theta is being multiplied by a number, okay? So it looks very similar to the circle equations, but here theta has a number being multiplied. If that number is even, like for example 4 and 2, it creates double the amount of petals. So if n were to be 4, then it's 8 petals. If n were 2, then it's 4 petals. If that number n being multiplied is odd, like 3 and 5, it tells you the exact number of petals, okay? And lastly, we have the Limassons, which I like to call the windmills or the infinity signs. And that is when the r is squared, okay? Do not expect to see the a squared in the actual equations. For example, if a was 4, you would just see the number 16, what 4 squared actually is, okay? But you can catch them by looking for an r squared, okay? Now, the sine are in the quadrants, depending on positive or negative, and the cosine is on the axis, depending on whether positive or negative. Again, the extent of the details of how to graph these is in 6.4 from pre-calc. So now we are going to move on to the calculus being applied to these polar functions, okay? So follow me here. If I'm going to tell you this new bit of information that r is going to be represented by a function of theta, f of theta, then I can take this old information that I knew from polar, that x is r cosine and y is r sine, and I can replace those r's with f of theta. And that's the notation that we're going to be seeing in calculus, okay? So if I were to use the derivative in polar form, okay, you're going to obtain it by using the parametric form and using the product rule. Now, you're going to memorize this, so don't stress about doing the whole product rule. The reason why they say product rule is because let's first look at parametric. Parametric we know is the derivative of y over the derivative of x. So if I were to do the derivative of y, I'd have f of theta being multiplied to sine, which I'd have to do product. So first times derivative of second plus derivative of first times second. Again, parametric over the derivative of x okay, I would have first times derivative of the second, that's where that negative came in, plus derivative of first times the second. Now, if you feel like that's too much to do that product rule every time, again, feel free to memorize, okay? We have f of thetas, we have cosine over sine, plus f primes, and then flip sine over cosine. The denominator has a negative, okay? And again, this is the derivative for polar functions. So before we see an example, let's go over some details here, okay? Well, actually, let me bring it a little down. If this dy d theta numerator is equal to 0, think back to when we learned the original, right? We learned derivatives, we learned the application. We learned that when the numerator was equal to 0, it was a horizontal tangent, and if the denominator was equal to 0, it's a vertical tangent. That's what 1 and 2 are telling you here, okay? If dy d theta, the numerator, is equal to 0 of this derivative, then it's a horizontal tangent. If the denominator dx d theta is equal to 0, then we can label that as a vertical tangent, okay? Now, if both are equal to 0, meaning the derivative is 0 over 0, that is an indeterminate, and we can call that no conclusion, okay? So, the steps we are going to take when solving these derivatives. Step 1 is we are going to change r to x and y, okay? So, for example, if they give us an equation of x equals r cosine of theta and y equals r sine of theta, I'm going to isolate the r's, okay? I'm going to plug the function given, the r equals, into these two spots and isolate the x and y. Okay, that's how I'm going to do that. And you'll see that as I solve the first example, guys. Then once we have it set up that way, we can differentiate with respect to theta. If this feels like a lot right now, just take a minute and write it down and compare these notes as we solve the first example. So looking at this first example, it says find the horizontal and vertical tangent lines of r equals sine of theta, okay? So if we're following these steps, we're going to change this r in terms of x and y, okay? If I know that x is equal to r times cosine of theta and y is equal to r times sine of theta, then this question told me r is equal to sine. I'm going to plug that into these two spots. So I can say x equals sine of theta times cosine of theta. There's my x function. And y equals r, which is sine of theta, times this sine of theta, which I can rewrite as sine of theta squared, or sine squared of theta, whichever one you like, okay? Now that I have everything in terms of x and y, and I want to know horizontal and vertical tangents, that's to do the derivative. Remember, derivative is written as dy dx. Since I turned everything into terms of x and y, I can go straight, like parametric, to do the derivative of y. So the derivative of sine squared, I have to do 2, derivative of the outside, rewrite the inside, subtract 1 from the exponent, times derivative of the inside. Derivative of sine is cosine. Okay, now dx, like parametric, I'm doing the derivative of x, all in terms of theta, right? I'm differentiating with respect to theta. I have sine times cosine, which means I'm going to have to do product rule. So I'm going to say first times derivative of the second is negative sine plus derivative of the first times the second. Okay? So now I can clean that denominator. I'm going to clean both. I'm going to say 2 sine cosine over, I'm going to write cosine squared minus sine squared. Okay, now if they ask me for the horizontal tangent, I'm going to be setting the numerator equal to 0, and then a vertical tangent, I'm going to be setting my denominator equal to 0. So I'm going to write my horizontal tangent will be my numerator, and then my vertical will be my denominator equal to 0. Okay, sorry about that. Fix my paper. So let's go over here to the left first. If I want to set this equal to 0, I need to isolate theta. So I'm going to divide by 2 first. If I divide by 2 on the left, it cancels out. And 0 divided by 2 is still 0. Remember, you learned this in algebra, that whenever I'm separated by multiplication, I can set each of them equal to 0. And now is when you need to have your unit circle memorized. When does sine equal 0? Well, that happens when theta is 0 and pi. Now over here, when does cosine of theta equal 0? Cosine equals 0 at pi over 2. And it also equals 0 at 3 pi over 2. But if we look back to the domain that they gave us, they only want us to go up to pi. So I'm only going to include pi over 2. Okay? So here's my answer for my horizontal tangents. Now, vertical tangents, set it equal to 0. I'm going to go ahead and move that sine squared over. Add it to the other side. And now that I have a single term on both sides and they're both squared, I can square root both sides. And I can say, when does cosine of theta equal sine of theta? But remember that when we square root, we have a plus or minus. So when does the positive or negative cosine equal the same as the positive or negative sine? Again, only on the top of the unit circle from 0 to pi. If you look at your unit circle, that happens when theta is pi over 4, that they have the radical 2 over 2, comma, radical 2 over 2. And remember, we don't care about the signs, so it also happens in quadrant 2 at 3 pi over 4. And you would be done with this question, okay? So what I want you to analyze is a few extra details, right? If maybe this question is asking for the ordered pairs, you would plug these back in to the original function, okay? Just like we did when we learned the application of derivatives and we wanted to know location, we'd plug it into the original function. We can also analyze the graph of this. The graph of this, let me scroll down a little bit, it's going to be the graph of sine, which we said the graph of sine in polar is majority top or all top because it's a circle. And the coefficient, which is 1, is going to dictate the diameter of this circle, right? This goes up here to 1. So now, notice horizontal tangents, let me draw them, should be here, and vertical tangents should be here. So notice this horizontal tangent could be the one they're talking about for 0 or pi, right? The one at pi over 2 is right up here. And now the vertical tangents, we know that the unit circle draws out a line at pi over 4. And you can see at pi over 4, here's the vertical. And then the other one comes right out here at 3 pi over 4. And there's the vertical tangent at 3 pi over 4. If I wanted to know, again, the ordered pairs, I would just plug it back in. So we'll say for horizontal tangent, okay, it's going to be 0, comma, plugging that 0 back into the original, which is sine. So if I plug 0 into sine, sine of 0 is 0. Now do the same thing for pi. Okay? Now remember, my ordered pairs are r comma theta. So my pi is going to go here, and the value of r is going to go here. Sine of pi is also 0. Last one, we have pi over 2. Pi over 2 is my theta, and remember it's r comma theta. So if I were to say sine of pi over 2, that would give me 1. Those are my horizontal tangents. Now for vertical tangents. I've got 2 of them. I'm going to plug these into the original. My ordered pair is r comma my theta. I'm plugging pi over 4 into sine. Sine of pi over 4 is radical 2 over 2. And now the next one. If I plug 3 pi over 4 into sine, then I also get radical 2 over 2. So they could ask this question of just the thetas. They can ask you the ordered pairs. These are your r comma thetas, the locations, okay? And then you could have to maybe match a graph and understand conceptually that that graph of r equals sine has these horizontal and vertical tangents. All right, let's take a look at this last question. Find the horizontal and vertical tangents to the graph of r equals 2 times 1 minus cosine of theta. So the first thing I want to draw to your attention is that I can rewrite this as r equals 2 minus 2 cosine of theta. And the reason why I want to think like that is because if you remember your graphs, I know that this, a number minus a number, is a Limasson. When A and B are the same number, it's the heart, the cardioid. And a negative with a cosine means it is majority left. So that means my graph is going to look something like this. So if this question has to do with horizontal and vertical tangents, I can already have a general idea that I have a horizontal tangent here and here. So there should be 2 of them, right? And there's a vertical tangent here, here, and here. So there should be a total of 1, 2, and 3 vertical tangents. So this is already giving me a heads up of my answers and what I should be looking for, okay? So let's go ahead and get started. We said the first step is to put this in terms of x and y. And if I know x is equal to r cosine of theta, then I'm going to go ahead and plug in this function into my r, and I can say 2 times 1 minus cosine of theta times cosine, which this cleans up to 2 times cosine of theta minus cosine squared of theta. Notice I don't put that 2 in. Remember, with derivatives and integrals, you can always just keep moving that coefficient down, which is why I choose to leave it on the outside, okay? So here's my x. Now, y is r sine of theta. So I'm going to put my r, which is 2 times 1 minus cosine of theta times sine. And if I clean that, I'm going to have 2 times sine of theta minus sine of theta cosine of theta. All right. Now that I have my x and my y, I can go ahead and do the derivative. dy dx, it's going to get a little complicated, but first I have to do the derivative of y, just like parametrics in the numerator. So I'm going to bring that coefficient of 2. Derivative of sine is cosine of theta minus, now here I'm going to have to do product rule, okay? So I have first times derivative of the second plus derivative of the first times the second. That numerator is a little ugly. We're going to have to work on that in a minute. Okay. Denominator, derivative of the x. This one should be a little easier. I've got the 2. Bring it down as a coefficient. Derivative of cosine is a negative sine of theta. Minus, here I have a chain rule, so I have 2. Rewrite the inside. Now it's to the first power. Times derivative of the inside, derivative of cosine is a negative sine. Okay, the first thing that I see that I want to start cleaning is that these 2's cancel each other out. Okay, now it's time to start simplifying. When I look at my numerator, I want you to be very careful that when you did this product rule, this negative needs to distribute to that first and to that second term, okay? So I have cosine of theta. Sine times negative sine is a negative sine squared, but with this negative becomes a positive sine squared. Okay, and then negative times positive is negative. Cosine and cosine make cosine squared. And as tempted as we are to think that we can use Pythagorean here, there is a minus, so I am not allowed. All right, now in the denominator, I have a negative sine of theta. Negative and negative make positive 2 cosine of theta. Okay, so now for my horizontal tangent, I'm going to want to set the numerator equal to 0. For vertical tangent, I'm going to want to set the denominator equal to 0. If I get a value that makes both of them equal to 0, remember that is no conclusion. Okay. All right, I'm almost done rewriting this. Okay, so we're done with our calculus pretty much. Now it's really just some algebra. Okay, this is messy. Okay, so if I can get this to read in all cosines, I could probably clean this up a lot. In Pre-Calc Chapter 5, you learned with the Pythagorean identity that you can rewrite the sine squared to say 1 minus cosine squared of theta. That's at the very beginning of Chapter 5. So now I can say cosine of theta plus 1 minus cosine squared of theta minus cosine squared of theta equals 0. I can combine these two, and it's going to say negative 2 cosine squared of theta plus cosine of theta plus 1 equals 0. Now this I can factor. I have a squared to the first power and then a constant. If this feels confusing to you, pause. Call cosine a variable you're used to seeing. Let's call it x, just for argument's sake. And now I can rewrite this as negative 2x squared plus x plus 1 equals 0. Now here you can use Pythagorean, you can factor. I'm not going to pause to go over factoring. If you need to watch a video of that, you can look one of those up. But here I'm going to take out a negative. When I divide the negative over, it disappears because 0 divided by negative 1 will stay as 0. I can create my two binomials. 1 times 1 is 1. Here I need a single x and a 2x. And then my signs, in order to make this a true statement, would have to be minus and then plus. Okay? If I set each of them equal to 0, I get x equals 1, and then x equals negative half. Now, remember, I had used that x to represent cosine. So now that I isolated it, I'm going to put my cosine back in, and I can say cosine of theta equals 1 and negative 1/2. Okay? So now I'm going to my unit circle. I know that cosine equals 1 at 0, and it equals negative 1/2 in two spots, at 2 pi over 3, and also at 4 pi over 3. This is how confident and comfortable you need to be with your unit circle. Now, they didn't necessarily give us a domain, but I know to look from 0 through 2 pi because this graph takes up from 0 all the way to 2 pi. It takes up the whole, like here's quadrant 1, here's quadrant 2, 3, and 4. It takes up all 4 quadrants. All right? So, done with the harder one. These are my horizontal tangents. All right, so now we're going to do the vertical tangent. I am going to take a minute, and I had missed writing the sine of theta because I had missed writing it here. And the reason why it should be there is because I did the negative and the negative, which is a positive, and I wrote the 2 cosine. I just had forgotten to write the sine, okay? So now back to vertical tangent. Notice that there is a sine in common in both terms, so I can factor that out and say sine of theta. If I divide it out here, I'm left with a negative 1 plus 2 cosine of theta. Remember, when I'm separated by multiplication, I can write each of them equal to 0. Here I can say, I can solve this already and say that sine equals 0 at 0 and at pi. And then here, I'm going to add the 1 over and divide the 2, so I can say cosine of theta equals 1/2. And that happens when theta is pi over 3 and 5 pi over 3. Now, before we close off this question, I want to bring your attention to something. In case you haven't caught it yet, you analyzed at the beginning that you should have 2 horizontal and 3 vertical. Okay? 2 horizontal, and I currently have 1 extra, and 3 vertical, I currently have 1 extra. That happened because there was a value that both made the denominator and the numerator equal to 0. You see how the number 0 came out twice? That means that at 0, there is no conclusion. Because when theta was 0, the numerator equaled 0, and so did the denominator. So we cancel that one out, and that is not one of our answers.